Going to be working the problems from section 1.2, graphs and lines, and we're going to be doing problems number 63 and number 65 on page 24. So the first problem, number 63, is a cost analysis problem. It says a donut shop has a fixed cost of $124 per day. I'm just going to write that down, $124 per day. And this is your fixed cost. And then it has a variable cost of $0.12, which is the same as 12 cents per donut. All right. This is your variable cost. So no matter what, this donut shop, to open the doors to the public, pay the electricity, pay their employees, is going to be $124 per day. And then it also costs them 12 cents per donut. And remember, these are costs, not profit. Find the total daily cost of producing X donuts. So your total daily cost is going to be your fixed cost plus your variable cost. So in this particular case, I'm going to call total cost T, and that's going to be your fixed cost, which is $124 per day, plus your variable cost, which is 0.12 for each donut. And we don't know how many donuts we're going to make, so we're going to need to represent that with a variable. So it's 12 cents per donut, so times X, and that is our total cost function. Now we could also change this T to T of X as like a function notation to make clear that the total cost is a function of X. You could also, if you want, change the T to capital C, which is probably more in line with what we want to do in this book, is use capital C for cost. But really it's just a variable. You have flexibility there in terms of how you choose that. So that's it. That's the answer to the first part. And then the second part is asking how many donuts can be produced for a total daily cost of $250. So remember, X is the number of donuts. They want to know how many donuts can be produced to have a daily cost of $250. So the question is, what does X need to be to make this $250? So I just replace this side of the equation with 250, 124 plus 0.12x, and then I go about trying to solve this for X. So the first thing I'll do is I will subtract, hold on, I will subtract 124 from both sides. So if I, where's my, there we go. Trying to grab my calculator in case I need it here. Excuse me. So I subtract 124 from both sides. Okay, and we're going to get, what, 126 on the left side? So we get 126 equals 0.12x. And then I'm going to divide both sides by 0.12. 0.12. So 126 divided by 0.012 on my calculator, I get 1,050 is X. So this is how many donuts I will need to produce in order to have a total cost for that day of $250. All right, let's look at number 65. So for number 65, we have, again, a cost analysis problem. And it says a plant can manufacture 80 golf clubs per day for a total, excuse me, I'm going to mute. Okay, a plant can manufacture 80 golf clubs per day for a total daily cost of $7,647. So 80, I'm going to put 80 clubs will cost $7,647 to manufacture. Also, they can produce 100 clubs, and that cost of manufacturing 100 clubs is going to be $9,147. Now, Part A says, assuming that the daily cost and production are linearly related, find the total daily cost of producing X number of clubs. So what they want is to know if we did X number of clubs, what would the cost be? And to do that, we're going to assume that this is a linear relationship. And because it's linear means that it's a line that describes this cost. And so graphically, what we have here is if this is the clubs that we're producing, and this is the cost, we know that at 80 clubs, we have a cost of, $7,647. So that's like a point, right? Like an ordered pair, 80, 7,647. And then we know if we produce 100 clubs, that our cost goes up. And so at 100, we have 9,147. So what we're going to do is we're going to come up with the function that draws that line. And to do that, we're going to use two formulas. First, we're going to get the slope of the line. And the slope of the line is rise over run. And that means y2 minus y1 over x2 minus x1. Here in this problem, we can label this point x1, y1, this one x2, y2. And then let's do some math here. We're going to take y2, 9,147, subtract from it 7,647. Oh, that's not so bad, 1,500. So this is going to be 1,500 on top. And then x2 minus x1, so 100 minus 80, that's going to give us 20. And when we divide by 20, we get 75. So we know the slope of our line is 75. And now we're going to use the formula, point slope formula, y minus y1 equals m times x minus x1. This will give us the equation of a line if we know a point and a slope. We have the slope of 75, and x1, y1 we know. So we now just plug in y minus y1, which is 7,647, equals slope, which is 75, and then x minus x1. x1 was 80. And now we have an equation. However, let's put this equation in the standard point-slope form. So slope-intercept form, which is y equals mx plus b. So let's get it to look like this. So to do that, what we're going to do is solve for y. We're going to get this y by itself. So I have to move this to the other side, but I also need to distribute this 75 through. So I'll do the 75 first. So we'll have 75x, that's when we multiply here. Then 75 times 80, negative 80, is going to give us negative 6,000. And then at this point, we will add the 7,647 to both sides. And over here it goes away. And over here you add and you'll get y equals 75x. And then that should be plus 1,647. There we go. So we could, if we want, write that our cost function, c of x, so I'm going to replace the y with c of x, is equal to 75x plus 1647. So this is the cost of manufacturing X number of clubs. So if we plug 100 in here, right, 100 in here, we get 7,500 times, or plus 1647. So that should give us $9,147. If we plug 80 in here, we should get this number. But now that works for any x. So we've come up with a nice linear cost function, and we can figure out how much it'll cost us to make any number of clubs. So that's part A, is getting the actual cost function. Part B is going to ask us, let's see, part B, graph the total daily cost for 0 less than or equal to x less than or equal to 200. So for part B, they want us to graph this thing for 0 less than or equal to x less than or equal to 200. So graphing this, we're going to have x, which is going to be the number of clubs, and then up here is the c of x, which is our cost. And to graph this, we have many different options on graphing this. We actually already had points, so we could graph those points. But I'm gonna do something a little bit different. I'm gonna use the fact that in this form, mx plus b, I know that the b is my y-intercept. So I know that this value right here is 1647, okay, $1,647. That is 1 point on my graph. That's what happens if we plug 0 in, right? If we plug 0 in, you just get that. So we know that. And then I actually know 2 other points, but I only want to go out to 200. So I'm going to actually go out to 200. I'm going to figure out where we would be. So I'm going to plug 200 into my function. So I'm going to do 75 times 200 on my calculator. That gives me 15,000, and then I'm going to add to that 1,647, which is obviously, what, 16,647. So $16,647 is what I get out here at 200. And then, because I know this is linear, I don't have a ruler in here. I have this, though. Straight enough. There we go. So I'm only graphing it between 0 and 200 because that's what it said to do. So that is my cost function on that interval. All right. We are done. That's it for this section. I'll move on. Next video, we'll cover the next section.